A common argument among flat earthers is the argument that if the world were a giant spinning ball, then fluids and loose objects on the surface of the Earth should be flung into space. After all, we've all felt the effect of centrifugal force when using playground equipment or on certain carnival rides. So if things are pulled away from relatively small objects when they spin, then they would certainly do so if the Earth was spinning, right? And since we aren't currently being hurtled into outer space, then obviously the Earth isn't spinning, but is instead stationary and flat. Case closed. Or is it? Can we really simplify the effects of centrifugal force to this extent? Is it possible to take a phenomenon we see on a small scale and infer that it must also be an effect on a large scale? Well, in some cases, yes, but never without first consulting the laws of physics. So let's go and do the flat earthers' homework for them and see what we come up with. But first, I should mention that centrifugal force is considered by some to be a misnomer. When you go on one of those carnival rides that spins you around, you get pressed up against the wall by what feels like a force pushing you outwards, which is often referred to as centrifugal force. However, what you are actually feeling is the force produced by the wall that prevents you from flying outwards due to your own momentum. This distinction is kind of inconsequential, but I wanted to mention it just to satisfy any physics term sticklers. Anyway, the equation that is used to determine the magnitude of centrifugal force experienced by an object is F subscript C equals mv squared divided by r. Let's break this equation down into its components. F stands for force, with the subscript C indicating that this is centrifugal force. The unit of force, in this case, is newtons. M stands for the mass of the object that is experiencing this force, and has a unit of kilograms. V stands for the circular velocity of the object, or how fast it is moving in a circular pattern. The unit that will be used for this is meters per second. And R stands for the radius of the circuit that the object is making, measured in meters. So let's apply this equation to a real-life example and see what we come up with. For M, I'll use my own mass, which is approximately 66 kilograms. Next, we need to find the radius of the Earth, which turns out to be 6.38 times 10 to the 6th, or just over 6 million meters. Now, using the radius of the Earth, we can determine the circular velocity of an object on the surface of the Earth as it spins. First, we take the radius and multiply it by 2 pi to find the circumference of the Earth. In one day, an individual standing on the surface of the Earth will travel the full length of this circumference. So to determine the velocity that they are moving, we just have to divide the circumference of the Earth by the amount of time it takes to travel that distance, which is about 86,400 seconds. Doing all the math, we find that the velocity of a person standing on the surface of the Earth is approximately 464 meters per second. So now we have mass, radius, and velocity, which means we can calculate the centrifugal force that I should feel if the Earth is round. And the answer comes out to about 2.2 newtons, which, for comparison, is just over 3/1000ths of the force of gravity on me. That is to say, essentially imperceptible. At this point, I need to add a quick caveat to this answer. You see, the only place on Earth where this example that we have looked at would be accurate would be at the equator, as any position north or south of that point would cause me, or any other object, to move in circles that are less than the full circumference of the Earth. This leads to an interesting phenomenon that I don't think even the most imaginative flat earthers can explain away. You actually weigh less at the equator due to centrifugal force than you do at the north or south pole, as you experience no centrifugal force at these points. This is called the Yacht-Voss effect, and has been experimentally demonstrated to occur even with very slight differences in latitude. All that set aside, the short answer to the flat earthers' challenge is no. A spinning Earth would not fling things into outer space. It would simply slightly reduce the measured weight of those objects by fighting the force of gravity. I think we can safely say that, instead of flying into space, we'll all stick around for a little while longer and enjoy our round world. Thanks everyone for watching this video. If you have any questions regarding the topics covered in this video, feel free to ask them down in the comments section. Additionally, if you have any topics that you'd like me to cover in the future, whether related to flat earth theory or any other sketchy topic that you've heard of, let me know in the comments, and I'll do my best to find some answers for you. Until then, get out there and enjoy our round world.